So, hi everyone. I just wanted to quickly go over a couple of quick tricks that hopefully will be helpful for those of you still working on the homework. There's a couple of ways in which you can design an experiment and define it in Minitab. Like typically, this I believe is something that everyone should be aware of. When you're working with the design of experiments in Minitab, it's sort of a three-stage process, right? So step number one requires you to create the design using our software. So this is under Stat DOE Factorial, Create Factorial Design, right? So you would first make a decision and say, I have three factors. I want to go here and say I want to do all 8 combinations of 3 factors at 2 levels, and I want to replicate it twice, right? So this is in the planning stages of a design that you typically need to create such design, say for 3 factors at 2 levels, low and high, for each one of 3 factors. You're doing all 8 combinations and decided to do replication. So this would be a total of 16 different experiments. You would go here under factors, and this is just to make sure, right, that you have the right factor levels. So for instance, even though that information is not provided, we got cutting speed, tool geometry, cutting angle. So cutting speed, tool geometry, and then of course you have the cutting angle. So 2 of the 3 factors are numeric. The geometry, I assume it would be text, and here, right in this section here with the lows and the highs, you would put the actual levels. Right now, this is a textbook example, so it's completely irrelevant. We're not going to be concerned about any of that, and that information is not provided in the book, so you don't have to do any of this, right? But if this was a real experiment that we were thinking about running, right, the first step, and this needs to be clear for everyone, is the first step is creating the design, and then Minitab allows you to have any number of responses, right? And here we would actually collect all data for all 16 runs, and then we would fit a model, reduce the model, and validate the assumptions, as we have been doing up to this point. Okay, but that's not what we need to do here, right? In this case, the design has already been created and executed for us. So you have 2 options, and I believe some of you already noticed that there's an Excel file provided on Angel that has all the data sets in Montgomery's DOE textbook. So one of the things you could do is simply grab this data, right, copy it. It has all 24 runs, and then just go into Minitab and click on the cursor in the first cell and paste it right there. So this would be the run order. Then we would have cutting speed, tool geometry, cutting angle, and life hours. At this point, Minitab doesn't know. It doesn't know that this is a DOE. Okay, and that's part of that's one of the reasons why in the homework we're telling you to use GLM, because GLM doesn't require you to define a design object. Okay, so you can use GLM as instructed. The output should be the same, right? You should get a regression equation, so that should not be an issue whatsoever. But to take advantage of some of the DOE functionality, it's better to tell Minitab, hey, this is a DOE object, recognize it as such. And this can be accomplished, right, by going under Stat DOE Factorial and choosing Define Custom Factorial Design. So this is basically saying I customized a design, or I created this somewhere else outside of Minitab. I'm bringing it in for analysis. I need Minitab to recognize it. So for Minitab to recognize it, because it was not created in our software, it needs to actually be defined. So this would be the option. Here you would choose the actual factors. There's only 3: cutting speed, tool geometry, cutting angle. From these 3 options, this is a 2-level factorial. Then you would click on low and high, and of course those are the levels. If we actually knew the levels, they would have been recognized here automatically, the actual physical levels for speed, geometry, and cutting angle. But that's not the case here. Everything's sort of a textbook example, so it's just coded in -1 and 1. Then you go under designs here, We don't have any of this information. The only thing that we have is the run order. We don't have a center points column. We don't have a blocks column that was previously defined. We don't have a standard order column. So all we know is the run order. These three columns, standard order, center point, and blocks, since they were not defined, they will be created by Minitab. And this is now recognized, right? This is now recognized as a DOE by Minitab. It knows it's a DOE. It knows that the only response is this one here, right? The only thing that was not part of the DOE object is life hours. So when you go to stat DOE factorial, you can go to analyze factorial design and put your response here. And the rest of it, right, it's straightforward. Creating the model, eliminating those terms that are not statistically significant, and validating the assumptions by checking the residual plots 4 and 1. I'm not going to show you that because that's part of your homework. Okay, so that's what you need to do. Alternatively, right, which is a lot more work, you can directly copy this information, right, from your homework. I can copy that, right? I'm copying that, and then I'm going into Minitab and I'm doing this. So I'm actually putting the actual 8 combinations here, the 8 combinations. So this I believe is completely irrelevant. Now this requires a lot of manipulation because these 3 columns, right, need to be repeated 3 times, and these 3 columns need to be stacked on top of each other. So I'll show you a nice little trick. If you do Control H will actually be a shortcut for replacing. Now if you don't like shortcuts, you can always just go to I believe it's Editor and then Replace. So the minus, I want to find the minuses and change those to a -1. I want to find entire cells only. So replace all. Here we go. What happened here? Well, the minuses changed to a -1. I'm going to do the same thing with the +1s. I'm going to change those pluses to +1s. And there we go. Now, why did I do that? Well, it's just to have the levels as instead of the minuses and pluses in the Word document. I mean, this is a little more intuitive, specifically when we look at the output. Now, one of the things I'm going to do here, and you can see that these were all text originally because they were just symbol characters. So one of the things I could do is actually change the data type. So instead of those columns being text, you may want to define them as being numeric, right? So A, B, and C. And I'm going to just replace A, B, and C. There we go. Now they're not text, they're numeric. And then the step to actually do the stacking. So I can use this little trick. Let's see. Stacking blocks of columns. And I'm going to say A, B, C, and I will be stacked on top of A, B, C, and 2, A, B, C, and 3. So this will do the stacking, and I'm going to call this new worksheet Stack DOE. Of course, as you're realizing here, this is too much work. I don't need the subscripts here. I just need to know that this is A, B, C, and this is life hours. This is the same DOE you could have actually gotten from that Excel file. Okay, so it's a little bit more work, but it's still hopefully these few minutes. If you don't care about doing it like that, you can just skip it. But at least you have a video that shows you the steps if you ever encounter a situation where you have to do some of that data manipulation yourself. At this point, once again, we would repeat the same steps that we showed before. Defining the 3 factors, A, B, and C, going under Designs and clicking OK. At this point, the design has been recognized by Minitab, so you can go to Stat DOE Factorial, Analyze Factorial Design, and go ahead and model the response, which is life hours. Okay, so enough of that. That was just a little bit of Minitab functionality. And by the way, this is no different in Minitab 16 or 17. This piece of functionality has not really changed. I believe the only thing that has changed, no, it's actually these would be exactly the same steps in Minitab 16 or Minitab 17. Okay, So I want to start with the new project here and just show you a couple of things. So what would be advantageous, right? In the book, I'm sorry, in the homework, we actually instructed you to use either GLM, right, to actually get the output. GLM and ANOVA and DOE are basically using the same math behind the scenes, so the results should be identical. Under certain circumstances, right? Could be that you get inverted signs. I mean, don't worry too much. It's just you get a mirror image of the output, which is exactly identical, right? You would be getting the same prediction values. You could see, depending on how you coded things, the things being flipped backwards, but it's not, once again, a big deal. What I'm going to do here is I'm going to open a project. Let me just quickly go through the mechanics here of showing you. So let's look at this. This is a very simple example that actually focuses on a DOE that has only two factors, temperature and time. And then we have two replicates, so it's a two factorial design, two-level, two-factor factorial design, 2 to the 2. It has two replicates for a total of 8 runs, and moisture as the response. So in this particular scenario, we can just go to stat DOE factorial. So if the design has been created and the Minitab and the data has been collected in that DOE worksheet, you can just go to stat DOE factorial, analyze factorial design. Moisture is the response. Under terms, you're going to see that automatically Minitab will fit all possible main effects and interactions. In this case, we would just go to graphs. And here, I believe this is slightly different in 16 and 17. In 16, you got to check Pareto charts of effects, or it depends on what your preference is, right? Those of you that use other applications might be a little more comfortable looking at half normal effects plots, or maybe normal effects plots. It doesn't matter. The inference will be exactly the same, right? The conclusion should be exactly the same. So if we click OK here, a Pareto chart tells me that any effect to the right of this threshold line, this red line, will be statistically significant at the 0.05 level of significance. So here, all main effects and interactions are statistically significant. The normal plot of standardized effects is showing that A and B have a negative effect, a negative standardized effect. If you think about it, temperature and time, we're increasing the temperature and increasing the time. What kind of effect that would have on the moisture of a cake? Of course, it's negative. As you increase the temperature, moisture goes down. As you increase the time, the baking time of a cake, the moisture would go down. But there's an interaction that actually has a positive sign, right? And all of these are statistically significant. You can see the labels here are showing a red little square that says that the effects are significant at the 0.05 level of significance. Now, also, for those of you, for instance, familiar with Design Expert, I believe Design Expert uses by default a half normal probability plot, or Daniel's plot, also known as Daniel's plot. And here, all the standardized effects, we take the absolute values, so we don't care if they're positive or negative. And here you can see that all of them are statistically significant, right? So this would be a very simple scenario where everything was statistically significant. The effect of temperature, the effect of time, and the temperature-time interaction. The R-squares are good here. You can see they're all over 90%. And your equation for prediction purposes would be right here. Right? So moisture equals 199 plus minus blah, blah, blah. Anyway, so that's the equation. Now, DOE offers, similar to what you guys saw before, the ability to predict with GLM, right? In GLM, we were able to fit a model, fit general linear model, and then we were able to predict. We were able to get factorial plots, so we were able to get most of these plots. The one that is actually different is the cube plot. The cube plot can only be found within stat DOE. And in one of the examples or problems in your homework, you're supposed to create a cube plot. So let's go over this really quickly. Factorial plots, really straightforward. We got, once again, the main effects and the interaction plot. If you wanted to do a cube plot, which in this case it would be a square plot because there's only two factors, it would look something like this. So you can see, for instance, if you usually when you have a cake, right, you don't want too much moisture or very little moisture. You want something in between. So maybe we're looking for a response that's somewhere here in the mid 20s perhaps. So perhaps close to 375 and a baking time of about 30 minutes. Okay, so this is the Q plot that you're being asked to complete in one of your homework problems. Okay, so one last thing here, and for instance, if you want to see the whole surface, there's this really nice little plot called the contour plot. The contour plot allows you to see the levels, right, for your response as you move in the design space. So for instance, say we wanted to get about 26% moisture. Well, this would be somewhere in this layer here, right? Somewhere here I get about 26% in the middle of this contour. So I can see there's an infinite number of combinations of temperature and time that would give me a moisture of about 26. Okay? So very well. So very similar. Now, you don't have to do it in DOE. Once again, you can use GLM. The only thing you would not be able to get from GLM is the cube plot. The cube plot is only available under Stat DOE Factorial and then all these features here. Okay? Very well. So hopefully this is useful for you guys working on the homework. And if you have any questions, please feel free to let me know.